Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is the capacitor. Our objective is to introduce the capacitor. We'll examine the basic construction of a capacitor, the units of capacitance and those properties that influence capacitance, interpreting and measuring capacitor values, and capacitors in series and in parallel. Capacitors are electrical devices that can both absorb and return a measurable quantity of electrical energy to a system. Capacitors store energy by accumulating charged particles on two conductive plates separated by a small gap. The gap is often filled with an insulating, i.e. non-conducting dielectric substance such as mica, ceramic, oil, paper, or a paste-like or liquid electrolytic compound. All these substances sandwiched between these conductive plates are assumed to be non-conductive in ordinary working conditions. The schematic symbol for a capacitor hints at the internal construction of a capacitor, being two parallel lines. These parallel lines symbolize the parallel plates with a small gap between the plates. You may also see capacitors represented schematically as a straight and curved line for reasons I'll explain in a moment. On a very basic level, a capacitor is a charge storage device, and a capacitor's ability to store charge is measured using a capacitance figure measured in units of farads. Capacitance is charge per unit volt. The concept of capacitance is symbolized using the letter C, and the units of capacitance are in farads, symbolized using an F. A farad is therefore a derived unit where 1 farad equals 1 coulomb of electrical charge stored per volt. It should be noted that the concept of charge is symbolized as a Q. Don't ask me why, and the units of charge is the coulomb, also symbolized as a C, where 1 coulomb of charge is equivalent to a group of 6.24 times 10 to the 18th charged particles. This choice of nomenclature is somewhat problematic because the concept of capacitance and the units of charge are both represented using the letter C. To prevent yourself from confusing the two, I typically write the concepts followed by the appropriate unit in parentheses. In summary, capacitance C in units of farads F is equal to charge Q in units of coulomb C per volt V in units of volts V. Trust me, I feel your pain, but that's the way it is. Let's examine a couple derivations of this relationship. Consider a capacitor full of 6.24 times 10 to the 12th electrical charges at 1 volt. Given 1 coulomb of electrical charge is a collection of 6.24 times 10 to the 18th particles, this represents a charge of 6.24 times 10 to the 12th over 6.24 times 10 to the 18th, or 1 microcoulomb of charge. This capacitor therefore has a capacitance value of 1 microcoulomb over 1 volt, or 1 microfarad. This might seem like a small capacitance value. However, understand that most commercially available capacitors are manufactured inside the picofarad to microfarad range. Consider the same 1 microfarad capacitor at an increased voltage of 25 volts. What happens to the charge inside this capacitor? Will it go up or will it go down? An algebraic rearrangement of our three-variable capacitor equation suggests that volts times capacitance equals charge. Substituting in our given values of 25 volts and 1 microfarads, we find that the same capacitor now stores 25 microcoulombs of charge, for a total of 156 times 10 to the 12th individual charges, 25 times as much as it did at 1 volt at 25 times the voltage. It makes sense. Let's consider another implication of this second algebraic manipulation. This derivation also suggests that a capacitor with a large capacitance value will store more charge at a given voltage than does a capacitor with a smaller capacitance value at the same voltage. Consider a 4.7 microfarad capacitor, also at 25 volts. This analogy may or may not be helpful. However, if you've got an understanding of hydraulics, capacitors are often like to accumulators in hydraulic systems, where an accumulator is a vessel full of pressurized fluid. Accumulators in hydraulic systems augment flow and stabilize the system by absorbing any sudden changes in pressure. Depending upon the application, capacitors might be included inside an electrical circuit to perform quasi-equivalent tasks. Consider this simplified buck chopper circuit, a power electronics device that steps down DC voltage. The moment the switch closes, current rushes into the system, a portion of which charges up the capacitor. The moment the switch opens, the DC source ceases to provide current to the system. However, the charged capacitor can now discharge itself into the load resistor. When this switch is closed and open repeatedly, resistive load in effect sees not on again and off again pulses of full current, but rather a relatively constant steady-state value. Returning to our hydraulics analogy, an accumulator with a larger volume can hold more pressurized fluid, and similarly, capacitors with larger capacitance values can hold more charge. Consider the size differential of a 3,300 microfarad capacitor and a 100 microfarad capacitor of similar construction. It makes sense that the 3,300 microfarad capacitor is substantially larger than the smaller 100 microfarad capacitor since it is intended to hold more charge. Depending upon the construction method and the material properties of the capacitor in question, this direct means of size and capacitance comparison doesn't always hold true, but for now just go with it. A larger vessel can hold more charge and a smaller vessel can hold less. A capacitor is a vessel into which you can stuff charges and at a later time withdraw them. This being said, note that capacitors include a small gap between the plates. As you are no doubt aware, current does not flow through an open. You might therefore initially assume that a capacitor blocks current flow. However, we'll learn that an uncharged capacitor experiences a brief surge of incoming displacement current during the charging process as charges accumulate on the plates. Additionally, a charged capacitor can supply a momentary burst of outgoing displacement current as charges are shed from the plates during the discharge process. We'll examine how the electrical properties of the circuit under inspection influence the intensity and duration of these bursts of current during the charge and discharge process in the very near future. Let's review our understanding of electrical charges. As you're no doubt aware, there exist both positive and negative electrical charges, and the ratio of these two charges influence the charge state of a larger object. Charged objects interact with other charged objects in a very predictable manner. The classic diagrams describing this behavior being two positively charged socks pushing each other away, two negatively charged mittens pushing each other away, and one positively charged sock and one negatively charged mitten pulling each other close. A capacitor in a discharged state is an empty vessel. This does not mean it's empty of charges, however. A discharged capacitor is electrically neutral because there exists an equal number of positive and equal number of negative charges on both plates. As such, there is no charge imbalance and there exists no voltage differential between the plates. If, however, there exists a surplus of positive charges on one plate and a surplus of negative charges on another, this capacitor can be said to be charged. The charge imbalance between the plates of a charged capacitor establishes a resulting voltage differential. Understandably, the greater the charge imbalance, the greater the voltage between the plates. It can be said that charge concentration directly influences voltage. More charge, more voltage. Less charge, less voltage. Theoretically, an ideal charged capacitor will maintain this charge imbalance indefinitely because the non-conductive insulating dielectric inside the gap between the plates prevents current flow and charge equalization. In practice, a real capacitor will exhibit a tiny amount of leakage over time and cannot be expected to maintain a charged state indefinitely. For now, let's just assume this is an ideal capacitor and no leakage occurs. As with all charged objects, an electrostatic field develops between the oppositely charged plates. The electrostatic field is normal to the plates, except for a negligible amount of fringing at the edges. The electrostatic field between the two charged plates is measured in units of volts per meter. Several conclusions can be made from these observations and our previous understanding of capacitance. Given the quantity of charge directly influences voltage, we could state that a large number of charges will result in a larger voltage differential, and given a larger voltage differential, we should observe a stronger electrostatic field. It makes sense. More charges, more voltage, stronger field. Coming at this from another direction, given quantity of charge directly influences voltage, we can state a smaller number of charges will result in a smaller voltage differential, and given a smaller voltage differential, we should observe a smaller electrostatic field. It again makes sense. Less charge, less voltage, weaker field. Other conclusions can be made. Notably, distance inversely affects the electrostatic field. Given a constant voltage between the two plates, it should be noted that by moving them further apart, we will lessen the electrostatic field. Conversely, moving the plates closer together increases the electrostatic field. This should make sense given your experience around charged objects. The electrostatic field around a charged wool sock, freshly pulled from a dryer, exerts itself quite strongly up close, but cannot be felt from across the room. In summary, more distance, weaker electrostatic field, less distance, stronger electrostatic field. An important observation can be made about the limitations of capacitors at this point. First, the electrostatic field in units of volts per meter places an upper limit of voltage that can be safely applied across any capacitor. If the electrostatic field ever exceeded the breakdown strength of the insulating material inside the gap, whatever is inside the gap can become a conductor and bridge the two plates. Accompanying this breakdown event is a large arc of current which equalizes the charge, often destroying the device in the process. As such, capacitors often stay at a maximum safe working voltage, under which the capacitor will function as intended, and above which, catastrophically, sometimes explosively fail. Consider this capacitor with a safe working voltage of 25 volts. At 25 volts and below, things are just fine. When I crank it up to 85 volts, things go south rather quickly. Another practical limitation of capacitors is the quantity of space available for charges on the plates. Charged particles take up physical space like passengers on a bus, and at a certain point the bus is full and there simply isn't any room for more charged particles. One way of increasing the charge storage ability of a capacitor is to simply increase the area of the plates. Larger plates result in more functional surface area and thus an increased ability to store charges. Conversely, smaller plates result in less functional surface area and thus a decreased ability to store charges. This supports our earlier observations that given capacitors of similar construction and material properties, the physically larger capacitor can store more charges at a given voltage and the smaller less. Finally, the influence of the dielectric material properties inside the gap on capacitors cannot be neglected. As we demonstrated, charged particles accumulate on the plates of a charged capacitor. While the insulating properties of the dielectric material does prevent current flow from one plate to another important phenomenon occurs. As we observed, an electrostatic field is established between the charged plates. Depending upon the material properties of the dielectric being employed, it can assist or permit the establishment of the electrostatic field through it in the following fashion. The dielectric, being electrically neutral, consists of equal number of positive and negative charges. The positive charges on the top plate attract the negative charges inside the top layer of the dielectric, and similarly the negative charges on the bottom plate attract the positive charges inside the bottom layer of the dielectric. As a result, an electrostatic field establishes itself internal to the dielectric, opposite of the electrostatic field established between the plates. Because of the dielectric influence internal to the capacitor, external to the capacitor, it appears as if a number of charges on the plates have found an equal and opposite dance partner. And as a result, more charges can accumulate on the plates at a given voltage. In summary, functional area of the plates, material properties of the dielectric, and the distance between the plates all affect a capacitor's capacitance value in the following fashion. A capacitor's capacitance value in units of farads F is equal to the functional area of the conductive plates A in units of meters squared times the relative permittivity of the dielectric in question, mu r, a dimensionless constant, times the permittivity of free space, mu 0, in units of farads per meter, divided by the distance between the plates, d, in units of meters. In terms of units, it makes sense. Meters squared times farads per meter divided by meters equals our resultant capacitance in units of farads. Before we make use of this equation, let's discuss permittivity and relative permittivity. Permittivity is an experimentally determined material property that quantifies how easy it is to establish an electrostatic field inside the material in question. The permittivity of free space has a value of 8.85 times 10 to the negative 12 farads per meter, meaning for every meter vacuum you cross, you get a capacitance value of roughly 8.85 times 10 to the negative 12 farads. Substances like mica have a permittivity that is 5 times stronger than that of free space, meaning the electrostatic field can be established inside mica 5 times easier. The relative permittivity, mu r, of mica is therefore 5. Get it? Mica permits the establishment of an electrostatic field 5 times better than vacuum, so mica's permittivity is mica's relative permittivity times the permittivity of free space, or 5 times 8.85 times 10 to the negative 12 farads per meter, or 44.3 times 10 to the negative 12 farads per meter. Other substances have different relative permittivity values. Consider a couple common dielectrics employed in capacitor construction. Oil can have a relative permittivity of 4. Porcelain can have a relative permittivity of 6. Tantalum oxide style capacitors can have a relative permittivity of 30. Ceramics, depending upon composition, exhibit a wide range of relative permittivity, with some ceramics having a relative permittivity of up to 7,500. Given our capacitance construction formula, it makes sense that if you wish to make a larger capacitor, you'd make the plate's functional area as large as possible, make the plates as close as possible, and stuff it full of some exotic ceramic with a high relative permittivity. Consider a capacitor with square plates having a side length of 2.54 centimeters or 0.0254 meters, roughly an inch by inch for the ignorant savages scavenging trash in the wasteland. This represents a functional surface area of 0.0254 times 0.0254 meters, or 645.2 times 10 to the negative 6 meters squared. Let's say the plates are separated by a distance of 1 millimeter, or 0.001 meters, and the space between the plates is filled with mica having a relative permittivity of 5. What's the capacitance of this capacitor? Substituting our given values into the capacitance construction formula, we arrive at a capacitance value of roughly 28.5 picofarads. What if we wanted a larger capacitance value? However, we're restricted to the same size package. Really, our only option is we'd have to swap out the mica dielectric for something with a larger relative permittivity. Let's say we employ tantalum as our dielectric. Substituting in our new relative permittivity value of 30 into the capacitance construction formula, we arrive at a capacitance value of 171.3 picofarads, 6 times the capacitance of the capacitor employing the mica dielectric, and 30 times the value of a capacitor made strictly with a vacuum between the plates. It makes sense. See if you can calculate the property of interest through the following capacitor combinations. Our first example asks us to calculate the capacitance of a capacitor with super large plates having the following dimensions: 5 centimeters by 15 centimeters, separated by 0.5 millimeters. Yes, you heard me right, 5 centimeters by 15 centimeters. Obviously, it'd be super hard to work with a device of these dimensions. For this reason, capacitor plates aren't necessarily square plates, but rather a long strip rolled into a cylinder, allowing the same functional surface area in a much smaller and more manageable package. Let's say it's filled with a dielectric that happens to have a relative permittivity of 30. Our second example asks us to determine the dielectric being employed inside a 128 picofarad capacitor with tiny circular plates having a diameter 0.7 millimeters separated by 0.2 millimeters. This will take some algebraic manipulation and knowledge of circular area calculations. By all means, pause the lecture and try these examples on your own. If you're struggling with the second example, here's a hint. Solve for relative permittivity. Here's another hint. Circular area is pi over 4 times the diameter squared. Use of these hints is admission of weakness on your part. If you're tracking, you should have arrived at the following values. For our first example, this capacitor has a functional area of 0.05 meters times 0.15 meters, or 7.5 times 10 to the negative third meters squared. The plates are separated by a distance of 0.0005 meters. The dielectric has a relative permittivity of 30, and the permittivity of free space is a value of 8.85 times 10 to the negative 12 farads per meter. Substituting our given values in the capacitance construction formula, we arrive at a capacitance value of approximately 4 nanofarads. Which brings us to a rather interesting challenge. Go to the stockroom and find a 4 nanofarad capacitor. Chances are you'll be looking for a long time because there is no such thing as a 4 nanofarad capacitor. For reasons that are completely beyond me, capacitor manufacturers only state capacitor nominal values in units of microfarads or picofarads and rarely, if ever, state the nominal values in nanofarads. This 4 nanofarad capacitor would therefore most likely be labeled as having a nominal value of 4,000 picofarads. Long story short, microfarads or picofarads only. I don't like this any more than you, but we're stuck with it, so we may as well get used to it. Moving on. For our second example, we've been asked to solve for the dielectric substance between the plates for a 128 picofarad with known dimensions. An algebraic rearrangement of the capacitor construction formula, solving for relative permittivity, suggests that relative permittivity is equal to the capacitance times the distance divided by area times the relative permittivity of free space. If this capacitor has a diameter of 0.7 millimeters or 0.0007 meters, it has a functional surface area of pi over 4 times the diameter squared, or roughly 384.8 times 10 to the negative 9th meters squared. Substituting our given values into the algebraic rearrangement, we arrive at a relative permittivity of 7,516. Most likely, some type of ceramic is being employed as the dielectric of choice for this capacitor. As I stated previously, capacitor manufacturers typically state the nominal value of capacitors in units of microfarads or picofarads only, and never state the nominal value in nanofarads. Because this will be an issue in the future, let's get some practice dragging this ball and chain around and smiling while doing so. Let's say you're presented with 3 capacitors having the following values: 0.1 microfarad, 0.068 microfarads, and 1,800 picofarads. Determine the equivalent capacitance value for these capacitors in units of nanofarads. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following conclusions. The 0.1 microfarad capacitor is equivalent to 100 nanofarads. The 0.068 microfarad capacitor is equivalent to 68 nanofarads. Finally, the 1,800 picofarad capacitor is equivalent to 1.8 nanofarads. Let's do the same exercise in reverse. Let's say you need a 33 nanofarad capacitor. However, you're presented with the following available options: 3.3 picofarads, 33 picofarads, 330 picofarads, 3,300 picofarads, 0.033 microfarads, 0.33 microfarads, 3.3 microfarads, 33 microfarads, and 330 microfarads. Which is the correct capacitor? By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following conclusion. The 0.033 microfarad capacitor presents the desired capacitance value of 33 nanofarads. The 3,300 picofarad capacitor would be 3.3 nanofarads, too small, and the 0.33 microfarad would be 330 nanofarads, too large. Again, I don't like this choice of units any more than you, but we're stuck with it and you simply gotta get used to it. If you're struggling with this concept, I'm suggesting you revisit the Engineering Prefixes lecture available at the Big Bad Tech channel. Moving on. I don't wish to dwell on this too much, but different capacitor construction techniques and differing dielectric chemical compositions influence capacitor performance characteristics. Certain capacitors may exhibit higher working voltages and others less. Certain types of capacitors might be more thermally stable, and others exhibit a wide range of capacitance values at different temperatures. Certain types of capacitors may exhibit a long lifespan, and other capacitors dry out and cease to function rather quickly. Long story short, there are different types of capacitors, and you can't expect one type of capacitor to be the best choice for any and all applications. We will be here all day if we start unraveling this thread, so I'll make this very easy. Based on an internal construction, you can divide capacitors into several general classes. Natural material capacitors, like those employing paper, glass, or mica as dielectrics, ceramic capacitors, plastic film capacitors, and electrolytic capacitors. Inside these general divisions, there are more subdivisions, and within these subdivisions are further and further subdivisions, but we are not diving that deep for the purposes of this introductory lecture. Above this level of distinction, another broader, more fundamental characterization can be made, and this is the take-home point. Natural material capacitors, ceramic capacitors, and plastic film capacitors are known as non-polarized capacitors, whereas electrolytic capacitors are known as polarized capacitors. These two types of capacitors behave differently and must be employed differently. A non-polarized capacitor is not orientation dependent, meaning it can be used with any polarity voltage, right side up or upside down. These types of non-polarized capacitors use two parallel straight lines as their schematic symbol. In contrast, a polarized, i.e. an electrolytic type capacitor, specifically designates one terminal for use at higher potential and the other for use at a lower potential. Polarized capacitors are orientation dependent. Polarized capacitors use one bent line in their schematic symbol to designate the terminal to be used at lower potential. Manufacturers use all sorts of schemes to identify the two terminals on polarized capacitors. For cylindrical polarized electrolytic capacitors with radial leads, typically the longer lead is the positive and the shorter lead is the negative. Additionally, a white or gray line, a negative sign, or a triangle, don't ask me why, is painted on the side can also designate the negative terminal. For example, here's a 47 microfarad electrolytic polarized capacitor. It looks like it has a safe working voltage of 50 volts, and the negative terminal is clearly marked with a bluish, grayish, whitish line, a negative sign, And if these marks escaped your notice, if you pull it out of the packing foam, you'll notice the negative lead is shorter than the positive. The curious among you may be wondering, what happens if you hook up an electrolytic capacitor backwards? Don't worry, you'll find out soon enough, because I've yet to witness a cohort of students graduate without having at least one of them do so. I should note that capacitors can also be classified by application. For example, special purpose capacitors might be called power factor correction capacitors, motor capacitors, and supercapacitors, which are a breed of animals themselves. Last but not least, I should probably warn you that unless a capacitor is large enough to have its nominal capacitance written legibly on its side, interpreting a specific capacitor manufacturer's code is a little tricky, principally because there simply is no agreed upon universal standard in doing so, as with the resistor color code. You'd think all capacitor manufacturers would adopt a single identification scheme, but they haven't, and it is the wild, wild west, and absolutely anything and everything goes, including colors, numbers, letters, and combinations of colors, numbers, and letters, where letters mean numbers, the numbers 8 and 9 actually have less value than the numbers 0 through 6, and the colors appear in 3-dot patterns, 6-dot patterns, and stripes. I am not joking about this. I could go down this rabbit hole deep as you wish, but I categorically refuse to do so because we've got a long way to go and a short time to get there. I prefer these lectures deal with practical electrical theory rather than untangling the thick witchery of capacitor codes. This being said, let's take a look at a couple random capacitors and introduce you to a means of reliably measuring capacitance value. Here's a non-polarized capacitor, most likely made out of ceramic, with the code 105K100JS written on the side. The numbers we're interested in are 105. This manufacturer is most likely using a 3-number code, where the first 2 numbers represent the first 2 digits of the capacitance value, and the third digit represents how many zeros you add to the end. This means the capacitor has a value of 10 with 5 zeros, or 1 million. What's the units? Picofarads, nanofarads, microfarads, millifarads, or farads? We're simply left to assume it's 1 million picofarads, since a 1 million microfarad capacitor would be ridiculously large. When 1 million picofarads is expressed using the most appropriate engineering format, this would be a 1 microfarad capacitor. There are a couple ways of confirming this. First, there exists a piece of special purpose test equipment called an LCR meter. An LCR meter is used to measure the inductance L, capacitance C, and or the resistance R of an electronic component. A simple LCR meter measures the device under test and displays a measured value. More advanced LCR meters can measure other properties, like the equivalent series resistance of capacitors and the Q factor of inductive components. Using a simple LCR meter is pretty easy. First, power it up and choose the capacitance function C. The capacitor in question is placed inside the test leads, respecting polarity if you're using a polarized capacitor. Importantly, note that the capacitor must be discharged prior to test. The LCR meter says 931.2 nanofarads, or roughly 0.9 microfarads, which is super close to the nominal value of 1 microfarad we interpreted using this manufacturer's shoddy code. Here's another example of the game of whack-a-mole you too may be playing one day when interpreting a particular manufacturer's means of identifying a capacitor's nominal value. Consider this small, non-polarized capacitor with the code 0.1, written in almost illegibly small print on the side. This manufacturer most likely isn't even using a code. The capacitor has a value of 0.1. What's the units? Picofarads, nanofarads, microfarads, millifarads, farads? Now we're left to assume it's microfarads, because as comically small as this capacitor is, 0.1 picofarads would be way, way too small. The LCR meter says 106.3 nanofarads, or roughly 0.1 microfarads, which matches the nominal value of 0.1 microfarads we interpreted using this manufacturer's shoddy identification scheme. Here's yet another example. Consider this cylindrical polarized capacitor with radial leads using a slightly more reliable identification scheme. It clearly states it's a 47 microfarad capacitor with a working voltage of 50 volts. It's obviously polarized because the manufacturer has taken the time to label the negative lead. The LCR meter says 42.2 microfarads, which is super close to the nominal value of 47 microfarads. Here's yet another example. Consider this cylindrical polarized capacitor this time with axial leads, also with a workable identification scheme. It clearly states that it's a 220 microfarad capacitor with a working voltage of 25 volts. It's obviously polarized because the manufacturer has taken the time to label not the negative lead, but rather the positive lead with a blurry plus sign. The negative lead has a black ring. Let's measure this capacitor using a different device. If your lab doesn't have an LCR meter, some DMMs have a capacitor measurement function that works almost like the ohm meter function. For example, the desktop Agilent 34405A digital multimeter has a dedicated capacitance measurement function. To measure a capacitor, an operator selects the capacitor mode on the faceplate and places the discharge capacitor in question inside the test leads. The digital multimeter says 201 microfarads, which is super close to the nominal value of 220 microfarads. Finally, here's a pretty hefty oil-filled capacitor, most likely intended for helping start a single-phase AC motor. It's not coy about anything, and the manufacturer proudly, clearly, and unambiguously states that it's a 2 microfarad capacitor with a safe working voltage of 440 volts AC, as well as a bunch of other pertinent data. If only every capacitor manufacturer could be so clear. Let's use a portable DMM to measure this capacitor. The Fluke 87 portable DMM can measure capacitance by enabling the secondary function of the ohm meter. To measure a capacitor, an operator rotates the selector switch to the ohm meter function and then presses the light blue or yellow secondary key. The discharge capacitor in question is placed inside the test leads, and the DMM says it's 1.98 microfarads, which is super close to the nominal value of 2 microfarads. Moving on, let's examine capacitors in series and in parallel. Capacitors, quite like resistors, come in standard sizes, and if you want a capacitor with a value other than one of the standard sizes, you're presented with two options. Option 1, buy an expensive variable capacitor and adjust it to the desired capacitance value, or option 2, use series and or parallel combinations of standard capacitors to obtain the desired capacitance value. Calculating capacitors in series and parallel is actually pretty easy if you remember this simple rule. Do the opposite you would if calculating resistors in series and parallel. To calculate the total capacitance of a series arrangement of two capacitors, C1 and C2, multiply C1 times C2 and divide it by the sum of C1 plus C2. If you're presented with a series combination of 3 or more capacitors, 1 over the total capacitance of this series arrangement is equal to 1 over C1 plus 1 over C2 plus 1 over C3 and so on. Finally, if you're ever presented with a parallel combination of capacitors, the total capacitance is equal to C1 plus C2 plus C3 and so on. Can you dig it? Calculating total capacitance of capacitors in series and parallel is the opposite of calculating total resistance of resistors in series and parallel. Don't make this hard. Consider a series combination of two 22 picofarad capacitors. Substituting these given values into the series capacitance formula suggests that the series combination has a total capacitance of 11 picofarads, or half that of an individual 22 picofarad capacitor. This makes sense given our earlier understanding of the capacitance construction formula, where capacitance equals area times the relative permittivity times permittivity of free space divided by distance. Given we link these identical capacitors in series, the bottom plate of C1 and the top plate of C2 would be at the same potential. If you think about it, all we succeeded in doing was doubling the distance between the top plate of C1 and the bottom plate of C2. Twice the distance results in half the capacitance. It makes sense. Consider a series combination of a 2.7 microfarad, a 6.8 microfarad, and a 3.9 microfarad capacitor. Substituting these given values into the series capacitance formula suggests that this series combination has a total capacitance of roughly 1.3 microfarads. This makes sense because our total capacitance of this series combination is less than the smallest capacitance. Finally, consider this parallel combination of two 820 picofarad capacitors. Substituting these given values into the parallel capacitance formula suggests that this parallel combination has a total capacitance of 1,640 picofarads, or roughly 1.6 nanofarads, or twice that of an individual 820 picofarad capacitor. This again makes sense given our earlier understanding of the capacitance construction formula, where capacitance is equal to area times relative permittivity times the permittivity of free space divided by distance. Given we link these identical capacitors in parallel, the top plates of both capacitors would be at the same potential, as would both bottom plates. If you think about it, all we succeeded in doing was doubling the area of the plates. Twice the functional area results in twice the capacitance. It makes sense. Try these example problems on for size. See if you can solve for the total capacitance of these series, parallel, and bonus round series parallel combinations of capacitors. Also, if you get an answer most appropriately expressed in units of nanofarads, try to convert it to the nearest picofarad or microfarad capacitor, because capacitors, for whatever reason, typically don't express nominal values in terms of nanofarads. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. The series combination of a 0.12 microfarad and a 0.56 microfarad capacitor results in a total capacitance of 98 nanofarads, which would most likely be expressed as 0.098 microfarads. The parallel combination of a 4,700 picofarad and 3,300 picofarad capacitor results in a total capacitance of 8 nanofarads, which would most likely be expressed as 8,000 picofarads. Finally, the series parallel combination of a 39 microfarad, a 15 microfarad, and a 6.8 microfarad results in a total capacitance of approximately 14 microfarads. Note it's necessary to first combine C2 and C3 in parallel with one another, a simplification I'm calling C single prime, then taking C single prime in series with C1. Finally, before I bring this lecture to a close, I want to drive a stake through the heart of a certain question that endlessly torments first-year electronics students. This question being, does current really flow through a capacitor? The answer is, kind of, but not in the traditional sense. Capacitors include a small gap between the conductive plates, and inside this gap is an insulating dielectric barring electron passage with the ferocity of Gandalf on a pipeweed binge. Under ordinary working conditions, any particular charge on one side of the gap or the other cannot, will not, and won't ever cross the gap. This being said, current can and does flow into and out of a capacitor. That's right, you heard me correctly. Current does not flow through a capacitor, but current can and does flow into and out of it. Allow me to explain. Current is the movement of electrical charges. You recall that 1 amp of current is the movement of 1 coulomb of electrical charges over a period of 1 second. Up until now, we've considered circuits incorporating only resistors at steady-state constant conditions. If a resistor draws 1 amp of current, it means 1 coulomb of electrons passes through it every 1 second. If we stood there and observed this circuit for 5 seconds, we'd observe 5 coulombs of electrons passing through the resistor. And if we observed it for 10 seconds, we would observe 10 coulombs of charge pass through. Current, however, needn't be continuous and constant to be considered current. Any displacement of charges, however brief, is also to be considered current. Note the term I employed, displacement. Consider an uncharged capacitor whose plates hold an equal number of opposing positive and negative charges. The moment a power source is connected to the uncharged capacitor, something interesting happens. The negative charges in the top plate are attracted to the power source positive terminal. Additional positive charges from the power source positive terminal move onto the capacitor top plate. Simultaneously, positive charges on the bottom plate are attracted to the power source negative terminal, and additional negative charges from the power source negative terminal move onto the capacitor bottom plate. Eventually, charging current subsides as effective area on the charging capacitor is reduced by the accumulating charges on each plate. Current into and out of the capacitor ceases, and the capacitor is now considered fully charged. Note if a dielectric is employed inside the gap, charges inside the electrically neutral dielectric don't leave the dielectric, nor do they permit conductivity from one plate to the other. However, charges inside the dielectric migrate to its surface to effectively cancel out some of the field of the charges on the plates. As a result, more charged particles are free to accumulate on the plates. This explains why capacitors incorporating strong dielectrics take longer to charge and can hold more charge than those employing weaker or no dielectrics. Note that during the charging process, an equal number of positive charges came into the top plate as those negative charges that left it. Similarly, an equal number of negative charges came into the bottom plate as those positive charges that left it. While it's true that no particular charge crossed the gap in the traditional sense of electrical current, this momentary movement of charges is still to be considered current. And to differentiate this type of current, the term displacement current is often employed. A suitable analogy for displacement current might be the collision of a couple billiard balls on a pool table. After a break, the cue ball doesn't land in the pocket. However, The cue ball does strike one colored ball, which strikes another colored ball, which strikes another colored ball, and eventually some colored ball lands in a pocket. A ball went in and a ball went out. This is displacement current, and it only happens as long as there's room. As more and more charges occupy functional area on the capacitor plates, displacement current slows down and eventually halts altogether. Again, while it's true that an individual charge on any particular side of the gap did not really cross the gap, this momentary displacement of charges is to be considered a burst of current. Charges came in at the same time charges came out. For all intents and purposes, it appears as if current flows through the capacitor during the charging process. Is it really true? Not really in the traditional sense. However, it seems that way. We're allowed to make this simplification. The discharging process is similar, only in reverse. A charged capacitor has an accumulation of positive charges on one plate and negative charges on the other. If no conductive path exists, an ideal capacitor will theoretically remain charged indefinitely. If, however, a conductive path in the form of a load resistor is placed across the terminals of the fully charged capacitor, the capacitor itself appears almost as if it were a DC power source. Difference being that the charged capacitor is not a limitless, continuous charge pump, but rather a finite vessel with a limited quantity of charge that can provide a momentary burst of current. The excess of positive charges in the top plate rush through the load resistor top to bottom to accumulate on the bottom plate. Simultaneously, the surplus negative charges in the bottom plate rush through the load resistor bottom to top to accumulate on the top plate. Following this initial surge of discharge current, the rate of charge transfer slows as the charge on the plates equalize. Eventually, charge movement halts altogether, and the capacitor is considered discharged. As with the charging process, any individual charge on a particular side of the gap doesn't really cross the gap. However, this momentary displacement of charges is still to be considered a burst of current. Charges came out at the same time charges came in. For all intents and purposes, it appears as if current flows through the capacitor during the discharging process. Again, is it really true? Not in the traditional sense, but it seems that way. We're allowed to make this simplification. Alright, that's about it for now. You may need to cool your brain after that last theoretical explanation and watch it again, or just forget it altogether, because when you get right down to it, the minute inner workings of a capacitor, while entertaining, really aren't that important for the transient analysis of the capacitor charging and discharging process. If you want a super easy summary of the process, here it is. An uncharged capacitor experiences an initial burst of current flowing into it. As the capacitor charges and voltage across the capacitor rises, current slows and eventually halts altogether. The capacitor is fully charged. During the discharging process, a charged capacitor supplies an initial burst of current out of it and voltage decreases. As the capacitor discharges, discharge current slows and eventually halts altogether. You can handle this simplification. We'll examine how the electrical properties of the circuit under inspection influence the magnitude and duration of these momentary bursts in later lectures. In conclusion, we introduce the capacitor, an electrical device that can store and return charges to an electrical system. We'll examine the concept of capacitance, inspected capacitor construction, and discussed how properties like functional area, distance, and dielectric composition influence capacitance. Additionally, we briefly discussed the shoddy and unpredictable means manufacturers use to label capacitor nominal values and how to measure capacitance using an LCR meter or capacitance measurement function on a DMM. Finally, we learned to calculate total capacitance of series and parallel relationships of capacitors. And finally, we discussed the somewhat complicated inner workings of capacitors during the charge and discharge process. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.